Hello, everyone. So today we have Steve and Greb talking to us. Steve recently retired from the Wisconsin DNR, where he worked as an aquatic research scientist for the past 32 years, addressing new and emerging environmental issues in the state. His work topics included acid rain impacts on aquatic ecosystems, impacts of cranberry marshes on receiving waters, thermal pollution in urban environment, effects of forestry, best management practices on stream water quality, Lake Michigan nearshore nutrient dynamics, and hydrologic impacts on changing climate conditions. Over much of the last 10 years, he is focused on the use of remote sensing to measure water quality from space. This rapidly advancing science has been used to measure water quality conditions in thousands of lakes across the state. And this work started as research here at UW-Madison through the Wisconsin IDEA. And it's transitioned into an operational effort at WDNR today. Steve is currently the director of the Group on Earth Observation AquaWatch initiative and has a research position here at CIMSS and is also an associate fellow at the Wisconsin Sea Grant Institute. So without further ado, give it over to
Thank you. Thanks, Zoe. Appreciate it. So yes, I worked at Wisconsin DNR for 32 years. It was a great job. It was my dream job, and I thoroughly enjoyed my work there for many years. I had one foot in the research world and one foot in the management world. So it was kind of a great place to be, and it was demanding, but an enjoyable job and rewarding. So today I'm going to talk a little bit about some of my efforts with my association with CIMSS here and at the Sea Grant Institute. The story actually starts here some years ago, I think actually almost 20 years ago. And it starts with the Wisconsin IDEA. And I told this story at the Wisconsin, the water day we had here this past year, but it starts with Wisconsin IDEA, and if you don't know what it is, basically, in a nutshell, it's taking the best ideas, the research which comes out of our universities, and transform it into applications or innovations towards solving problems within the state of Wisconsin. So, 20-some years ago, there was a researcher here in this building who was working in the remote sensing field. His name was Jonathan Chipman. I don't know, most of you look pretty young and maybe didn't know Jonathan Chipman, but he was a researcher here. So he had this idea of, by the way, this is Jonathan Chipman now. I think that picture does look a little bit like Jonathan Chipman, but a little older. So he had this idea of, can we use satellite remote sensing to measure water quality in the lakes of the state? As you know, we have over 10,000, 15,000 lakes in the state, and being understaffed and undermanned and underfunded at Wisconsin DNR, it's hard to get out and measure the water quality in all these lakes. So if we could find a tool that would help us measure these lakes in a more cost-effective way, we wanted to pursue that. So hence this lakesat.org was formed. Before I get into too much of the details of that program, just a few slides on remote sensing of water quality and how it works. Basically, these are passive systems. We're not using laser or active systems to excite the molecules within the water, but we're using the sun and the energy of the sun. It's the passive system. So the sun comes in here on your right side. Some of it goes into the water columns. Some of it gets reflected back off. That light which goes into the water column interacts with some of the water quality constituents within the water column. The only things we can measure by remote sensing are things we say are optically active, things that are interacting with the light and that will modify the reflected signal. So, and they can be things like phytoplankton, suspended solids, turbidity, stuff, solid material within the water column, and the colored material, or the DOC, dissolved organic carbon, or sometimes referred to as CDON. A portion of the signal hits the bottom, is reflected back too, and we don't like that. We don't want the satellite looking at the shoreline that's an interference. We want to look at strictly the water column, because we want to know the concentration of the water in the water column, not the signal of the color of the bottom itself. So some of this light emerges back out of the water. We call this emergent flux, and then hits the sensor at the satellite. There's a lot of other stuff going on here. A lot of the light is bouncing around, and specifically what's most important and of concern to us is the scattering of the light in the atmosphere. Atmospheric correction is a huge issue, and it probably is in other fields, but in terms of water, measuring things in the water quality arena, the scattering of the light, and I'd say it's a lot of research now is focused on this atmospheric correction component, because it can way overwhelm the actual signal coming through from the water itself. So if we looked at the reflectance of the sunlight that's coming off the water from the water column, this is the plot we would see if we use a spectroradiometer. We look at what's going on in the visible wave bands. So we see, as you see, there's a number of troughs and peaks here, and these are indicative of water quality constituents. These peaks here, TSM is total suspended matter. You can see these peaks, and they always take place at certain wavelengths. And then there's also these troughs. This one is indicative of chlorophyll. And this would indicate actually fairly high chlorophyll. This trough here would be phycocyan, the blue-green algae that are affecting our lakes that are, can have a toxicity effect, and is one of the main water quality constituents that we're concerned about today. So we exploit this graph in terms of its peaks and valleys, and we use this to quantify the water quality constituents based on a number of different mathematical expressions. It can be peak height, it can be area, it can be a number of things. It can be slope, or first or second derivative, and the expressions are everything from empirical expressions to semi-analytical, more complex mathematical formulas that approach this. So, at any rate, but this is what we start with. If we were to look at that same plot, but we've overlaid it now with 4 of the sensors that are commonly used in the water quality field. So these are the 2 current Landsat satellites, Landsat 7 and Landsat 8, and the Sentinel-2 and Sentinel-3, which are part of ESA, the European Space Agency. Sentinel-3 being a coarser resolution than the Sentinel-2. And what you can see, these kind of gray bars here represent where the bands, the sensor bands are. They're both their placement and their width of what they're measuring in terms of wavelengths. So you can see the Landsat, especially Landsat 7, these are pretty wide width bars. And so as you're trying to quantify what's going on, these peaks and valleys, it's pretty tough when you have these wide bars to relate the value of, say, band 2 to a peak here, because it includes both the rising and falling limbs. So the Europeans now have designed these satellites that have more bands and narrower bands. And they also have bands which are actually focused on these peaks and valleys. So now we're starting to get a lot more, we're starting to see a lot more accuracy in these algorithms, and we can have targeted bands for these peaks and valleys. And so the expressions are getting better, or the equations are getting better, the accuracies are getting better. And this has all taken place just in the last couple of years here. So, so this science and the technology is evolving quickly, and we're starting to see changes on a monthly basis. So it's a pretty exciting time in this field. So what are some of the advantages and disadvantages of doing this? And I've touched on a few of them. But we can go out in northern Wisconsin, not us, but the satellite can be flying over, and with one snapshot and one image, relatively high spatial and temporal resolution, we can get a snapshot in time of 1,000 lakes. And so we can see what's going on in those lakes, again, at one specific time across the landscape. And it's relatively affordable. You know, if we had to send someone out in a boat with a little Secchi disc, and that's basically what we're talking about here in Wisconsin, we're measuring water clarity with the depth at which you can see a round disc. I'll show a picture here in a moment. But it'd be quite expensive. We had to send teams out every summer to do this. Historical data for studies of trends in water quality. So there's a large archive. There's this legacy of the Landsat satellites that goes back many years. We can go back and look at we can collect these imagery and actually see how water quality is changing over time. Fourthly, again, with some of these newer satellites, we're actually starting to develop early warning systems for things like harmful algal blooms. What are the disadvantages? Well, we here in Wisconsin and a lot of the inland waters are highly complex. There's a number of constituents, optically active constituents that are in the water, so it's a soup. So it's kind of hard to, break out the individual constituents because what the satellite is seeing, of course, is an integration of all these things. So it's a little tougher to get a clear signal and to get clear peaks and valleys from that earlier plot. We have potential interference from the bottom. We don't want, as I said before, we don't want to be looking at the bottom of the lake and seeing what color the bottom is. We just want the color of the water column itself. So when we go in and analyze these images, we have to cut out the shallow areas. Clouds are a nemesis. They're bad news in my business. I know for some of you probably work on clouds and you love clouds, but for us, there's many times when 40% of the time that the Landsat flew over, we had cloud cover in Wisconsin, so we just don't get images on those days. We can't see through clouds. Dynamic changes in water quality. So, like these events that we've recently had, where there's big changes in 24 hours or 48 hours, when you have a Landsat satellite which is flying over every 16 days, it's pretty tough to catch those changes. We can only see, as I said before, things that we consider optically active, so at least it's a limited number of parameters. And also, we still need people on the ground to take samples for calibration and validation. So the system that was set up at Wisconsin DNR, again, we're talking about Secchi disc or water clarity. This is an indicator, again, of the trophic status index. We actually we use a citizen-based monitoring program in the state. So we train citizens how to take a number of measurements, how to take their Secchi disc. We give them a calendar which has all the dates that the Landsat is flying over. So they got those Secchi in their calendar and they're ready to go. And then when that day comes, they go out in the center of their lake at a pre-described flat and long and take a water clarity measurement at the time that the satellite is flying over. These green dots that you can't see very well, they're locations of the lakes where we have citizen-based monitoring efforts. So we have something now, I think it's somewhere between 800 and 1,000 volunteers that go out on a monthly basis and take samples for us. So it's a great program. We couldn't do it without it. And then we use, again, their values and match it up with the values from the satellite, the digital number from the Landsat in this case. And in this case, we're using a model which has band 2 or band 4. And you can see how there's this linear relationship with the log of the Secchi disc. So those are the kind of models we use. And then from that, we generate, again, these water clarity maps in Wisconsin. This would be a map of northern Wisconsin. And as you can see, as you look across the landscape, these lakes are color-coded by their water clarity values. And you can see there's quite a variety. It's kind of this mosaic of different water clarities across the state. So it's pretty neat. So this is open, this is obviously, it's public records, and you can go in here and click on your lake and see what your water clarity is, not just currently, but over the past few years. And you can actually look at variability within a lake too, clicking at various spots within the lake. You can play a number of games. These are just some simple plots looking at the distribution of water clarity in our state. The mean water clarity is roughly, it's just a little bit over 9 feet, about 3 meters for the state of Wisconsin. And as you expect, the water clarity increases as you increase in latitude. As you go up north, you know, there's a lot of clear saltwater lakes in Wisconsin. And as you can see, water clarity, the Secchi disk is quite variable on small lakes across the state, but as you go out to some more large lakes, there's kind of this asymptotic trend where they're fairly similar in the large lakes. And again, these large lakes would probably be lakes at the bottom of the watershed, bottom of the landscape, so they're kind of integrators of everything above. Just another slide just showing the 4 satellite sensors that we've been employing here. And as you can see, this shows potential. You know, purple is suitable and green is highly suitable. And as you go to left to right, you can see that this Sentinel-3 is the most highly suitable for water quality. The downside to the Sentinel-3 is it's a large pixel size. It doesn't have the spatial resolution as, say, Sentinel-2. So you're looking at 300 meters, which on small lakes it just won't happen. So I'm going to switch gears now and talk about the AquaWatch initiative, which is the water quality community of practice within GEO. And I don't know how many of you are familiar with GEO. GEO is a group on Earth observation. It's a large organization. There's over, I think it's up here, there's 105 nations now signed on to it and over 100 international organizations, so it's huge. And GEO basically is trying to build what's called GEOS, which is this framework. GEO isn't about generating or producing new data, but it's linking data. It's bringing data together in disparate sources around the globe and trying to bring it together into an interoperable database. So GEO is broken up into what we call societal benefit areas, and so you can see there's a lot of areas that they address: disasters, health, energy, climate, agriculture, ecosystems, and then down here in the bottom is water. And so that's the SBA that I work within, that water quality falls under. So what is a community practice? It can mean a lot of things to different people, and I think it's all these things on this chart in terms of bringing people together, trying to identify solutions. When we formed this community practice, a lot of people said to us, well, this is really the first time that this community has gotten together. And so GEO, you could say, is not just about linking data, but it's also about linking people. So just by getting all these folks together, it's paid off with dividends. But basically, this community practice is getting people together who share a concern or passion for something, in this case, water quality. It's bringing together a number of different practitioners from different disciplines or areas related to water quality, and how do we measure water quality better, and so we engage this group on a regular basis. So we have participants from state, federal, international governments, the private industry, private consulting groups, nonprofits, a lot of UN organizations are part of our group, and of course academic institutions. So the mission of AquaWatch, this is kind of the high-level look of it: improve the coordination, delivery, and utilization of water quality information for the benefit of society. I mean, you could ratchet up even further and say, we're in this to preserve and protect water quality for human and ecosystem health. So that's kind of the high view of this. And we come down a little bit, again, it's more focused on building this global capacity and utilizing the Earth observation derived water quality data products and information to again, help support water quality management, decision makers, and a number of other end user communities. Within AquaWatch, we have five working groups. We have that follow these 5 objectives. We kind of follow this model, this kind of end-to-end model on the top, where we start with the end user, trying to understand their needs, and we engage them to, again, develop what kind of products are they looking for, how can we be useful to their community, observation of data. This is kind of at the satellite level, the sensor level, developing better sensors, better algorithms to interpret the imagery, what kind of products can we make from that, what kind of products are needed by the end user, and then how do we get this out, what kind of dissemination or access and visualization tools can we make, how can we make this easier for the end user for use and interpretation. And then of course, we have an education and capacity building working group also. One of the current activities, I'll touch on some of the other ones here in a minute, is we're working on something called this Water Quality Information Service project. And essentially, we want to build what we call an operational water quality information system globally. And as you can imagine, that's a big job, and we're taking it in small steps here. But we do have this focus on the developing world because they don't have the infrastructure that we have in terms of monitoring and management. And how can we build these tools here and transfer them to these developing countries through capacity building efforts. So this is a series of steps we're going through with these work packages, and I'm not going to spend much time on this, but to say we're in this work package 3 and 4, where we're now developing single products for global scale use and developing these end-to-end demonstration projects. This is just another organizational structure, how we could visualize this water quality information service in the center. And then these 5 working groups are feeding into the information center and also interacting amongst themselves. I'm not going to touch on this as the governance structure. So every other year we meet face-to-face. We have quarterly meetings too, but every other year we meet face-to-face. We met this past summer in Stirling, Scotland, in conjunction with the Global Lakes meeting that was going on. So we got together and talked about our next work plan and what we're currently involved with and what we plan to do the next 2 years. Again, just to give you some sense of the kinds of things we're involved with. Developing a kind of a decision tree for an end user to come in and say, okay, I want to use remote sensing. How do I do it? Or how do I get started? So it talks about what you want, how frequency, in terms of spatial and spectral resolutions, temporal resolutions, what are your demands, things like that. And this will give you a list of what satellites are available, what software is available, what products are out there for you. We're doing a survey of the training needs now. We want to get more involved in demonstration projects. We're, of course, constantly working on our website, and we have a webinar series which we run about every other month globally. On the observation and data, etc. side, we're doing an inventory now of which we've done one for the past 3 years, but we're constantly being updated as to what is out there, what kind of satellite-derived water quality data is out there, and then what's the nature of it in terms of was it a one-time deal, one-off deal, or is this going to be updated annually, or how often is the data put out, or what are the requirements in terms of its usage, things like that. So again, we're kind of compiling this for our community. Library of algorithms, of course, algorithms really are at the heart of generating these products. And we have a review paper we're working on now that will reflect this library of algorithms and what's available and who's doing what. Optical standards for optical properties. I showed that a couple of those slides where we looked at the radiometric properties of the emerging flux, radiance. There's a lot of different instruments out there, and when we're starting to use this kind of data for validation efforts, there needs to be some calibration amongst those instruments and some standardization of the protocols. So that's something which really hasn't been done for these inland waters. It's been done for some of the ocean waters, but not so much for the coastal. There's a lot of citizen science effort. Citizen science play a big role in the water quality area. SDGs, you don't hear much about it here in the States, but these are the Sustainable Development Goals that the UN has out, and it's a huge effort globally right now. And I think satellite remote sensing could play a big role in understanding or using. What they're after is looking at indicators of water quality within countries and regions, and I think you'll see remote sensing play a big role in helping fulfill those monitoring requirements. And then validation is a big need. We have a lot of people that are putting data products out there, both in the private sector and from some of the agencies around the globe. But there isn't a lot of in situ data to see how good these numbers are. And so we really need more validation efforts. So we have right now we're in the process of getting a postdoc at Goddard Space Center. And that person, we're hoping, is going to focus on the validation work and maybe even develop a global validation effort, which could be huge. I just wanted to touch on the AeroNet OC, which is AeroNet Ocean Color. I don't know if many of you are familiar with AeroNet. You guys have an AeroNet site on your roof here. I think Brad Pierce is the point of contact for that. So within AeroNet again is this aerosol robotic network, and it's measuring atmospheric aerosols and so things that are important for us, but they're important for a lot of atmospheric work, obviously. So within AeroNet, there's a subnetwork called the AeroNet OC, and besides the sun photometer pointing up at the sky on a 10-minute basis, the arm rotates and it points at the water, and so it actually measures the emergent flux from the water itself. So it's pretty neat. So it plays a couple of roles. So as it says, these are autonomous radiometers and fixed platforms. Identical measuring systems. These are all sent back in every winter, and they're all referenced, calibrated, the same standards, and they all produce standardized products like normalized water, gradients, aerosol optical thickness. So we've been pushing to get one here in Wisconsin, and then just this past year, they released 3 new, they're called sea prisms as an instrument, 3 new sea prisms, put them on inland waters, which is kind of a new thing. All up till now, most of these AeroNet systems, the ones over water, have been in saline or in coastal areas. So they have 3 inland waters, one in Florida, one in Lake Erie, and one in Green Bay. So this is the system here in Green Bay. That was just installed this past year. This is what it looks like up close. This is the crew. This is a collaborative effort with New Water, which is out of Green Bay, and we do the monitoring for Green Bay Metropolitan Sewage District, so we have this cooperative agreement, we use their boat. I'm taking this picture up on the platform up here now. So here's we're installing the new AeroNet system in Green Bay. This is what it looks like. These are spikes for gulls. Gulls are a big issue with this. It's nasty, and we've actually had them come and tear these spikes off. I mean, these are tough characters, and but you need to protect this because, as you can imagine, there's bird poop everywhere on this platform. That's why I have the tarp down, and it's pretty corrosive if it gets on your equipment. So you have to keep this stuff clean and keep bird spikes to keep the birds away. This is at the Angle Lighthouse, which is about 5 miles from the entrance to the Fox River. This is a shipping canal, so there's big ships that go by all the time. I just wanted to point that out. So I think I'll quit there. If any of you are interested in this work or interested in joining one of our working groups, please, well, it'd be best just to talk with me or Mary Beth Mealy is our secretary of the position. This is our website. So with that, I'll quit. Thank you. Take any questions.
Could you describe the difference between a healthy looking lake compared to one that's not?
Well, it's interesting. I guess it's your definition of healthy, whether it's in terms of, generally, one of the yardsticks is this trophic status index. So it could be the amount of chlorophyll, amount of turbidity in the water, or just the amount of clarity of the water. It's a little deceptive because it's not an easy answer. I'm not trying to be evasive here, but you might take a lake like this, which I would be looking at it, Jesus, that's a healthy northern Wisconsin lake, and it probably is considered a healthy lake, but it's not maybe a very productive, or you wouldn't catch a lot of fish out of it. That's your definition of healthy. This might be a very stained lake, would be my guess. And so we would consider that a dystrophic lake, but there's a lot of staining, so which again impedes some of the productivity, might have to be low in nutrients. But there are general indicators that are used for water quality, trophic status, and that's probably the most common ones.
What height would, or I guess what depth would you say is usually where you can't get good information on for a given lake?
I mean, in terms using the satellite remote sensing?
Yeah.
So, the satellite will see as much as the light can penetrate the water, obviously. So it's not necessarily a question of how much. Actually, in some ways, you're better off with a more productive lake that has a lot of stuff in it that you can measure, has a higher reflectance signal than we call a oligotrophic lake, or a lake which is very clear. It's really hard because there isn't much reflectance, so your signal is really small. The exception to that is if you have a really high productive lake, sometimes you get scums, or you've probably seen it on Mendota here. Last year they had blue-green bloom like in University Bay here. So that scum really isn't reflective of algae in the water column. It's kind of a localized issue. So, but we measure, say, this water clarity from space. There'll be values in there of 10 centimeters or 0.1 meters. So it could be this much to, I think some of our lakes, we have values of up to 15 meters or something like that. Again, those are estimates, so it's pretty hard to get a good value exactly.
You mentioned some of the high latitude applications. If you look at nutrient flux from, say, glaciers, right, you see a real strong signature of like nutrients and productivity near these community moraines that I go out and do. Is that the sort of thing that you're able to capture on with this, or is this more focused on just like lake water quality?
No, I mean, AquaWatch is, I mean, our community is focused on both inland and coastal waters. So everything except oceanic waters, put it that way. So nearshore waters. So I think what you're talking about is, you know, plumes that are going out from these washes. Yeah, and depending on what that is it inorganic material or is this?
Oh, yeah, I don't know.
Right, and some of that, again, if you look at the signature of the reflectance, you know, the peaks and valleys, you can determine some of that. You know, see what, you might have a high TSM signal, but you also have a sharp chlorophyll trough too, which says, yeah, you get a lot of material there, and a lot of it is actually green material. So.
The algorithms you have are more tuned towards like chlorophyll, that like the standard thing you're looking at are more.
Yeah, standard things we're looking at, and I don't know, I wonder if they one. Oops. Now what do I do?
Where are you looking for?
It's about halfway down. Oh, that table. Oh, above that. Yeah, that one. So this had just some of the things that chlorophyll, phycocyanin, TSM, CDOM, color, Secchi-Dis, transparency, vertical attenuation light, those are the kinds of things we're generally, interested in. So, and I should have pointed that out. I mean, satellite remote sensing isn't, you know, the silver bullet, or it's not this panacea like we can solve all these monitoring questions, or we can monitor everything, because especially things that are dissolved, you know, some of the nutrients, salt, pesticides, you know, metals, we can't see that in satellites. I mean, I doubt we ever will. So again, it's just focused on things that are out there, touching things.
Can you estimate the temperature of the lake water?
Yeah, we're actually really good at that.
Yeah.
I didn't touch on that because I was just dealing with the visible bands here, but yeah, the infrared bands in Landsat. Sentinel-2 doesn't have it, I think Sentinel-3 does have the thermal bands. But we're actually pretty good at that, and we've done that in northern Wisconsin, which is pretty interesting to just take a snapshot. Again, I use the word snapshot, but I mean just one image for, you know, northern part of the state, and look at how these lakes really vary in temperature on a given day. Of course, a lot of it's a function of how deep they are. Some are really deep lakes, some are shallow. Cranberry beds really stand out. I mean, you can see they're warm.
Well, would the temperature be typical of the surface, or would it be some reflection of the whole lake?
You hit it on the head. That's a big issue. That's why a lot of people haven't been using it, because the sensor essentially is measuring skin temperature, we call it. You know, it's just the top micro layer in these thermal bands. So if your lake is well mixed, you know, or it's a windy day, then it would indicate more of the water column. If it's perfectly calm, then where you're going to have stratification, it's not going to measure that.
Oh.
Anything else? Yes.
So you mentioned bottom reflectance and the impact on your estimation of those products up there. How do you determine really where that's happening? Does that involve making assumptions about the chemistry of the lakes?
So, right. So we're lucky here in Wisconsin in that we pretty much know our lakes. We know what the depths are of our lakes. We know the location of that deep point. And what we generally do is we own, how could I say this? We know the depth of the lake. Say if the lake depth was 10 meters, we would only report a secchi if it was 5 meters or less, just to be really conservative about seeing into the bottom. So we know the deep point. We're only measuring a, say, a 9x9 pixel in that deep spot. We're not doing it around the whole thing to do this calibration. So, and you're right. So you have to exclude the shallow areas, but we don't. Again, if a lake is really clear, we're really suspicious about even using that, either in our calibration or reporting it out. And we'll only use seccas that report seccas that are like 50% of the total depth reported in the total depth. I don't know if that confused you or.
I'm curious about citizen scientists and contributions. So I looked at Kyle's and took a photo of the plume, the gutter wash that came after strong rain. And now I'm thinking that you correlate that with the metadata for the date and time of that photo versus the amount of rain that we got that day, and then measure the plume. The second part of the question might be, do you put sensors close to these outlets that would be known outlets and known things for the cities? Or the civil engineering might affect the particular community.
So I'm not sure I understood your question. Could you put sensors out?
So is it worth it for citizen scientists to bring up old pictures, give them metadata, and be able to access that weather for that day? Is that significant at all or irrelevant? And also, are sensors placed near outlets, known outlets for cities? Because it was troubling to see this plume of water. I was wondering if somebody's automatically placing sensors. So you're saying places in places that are deep enough, you have your requirements.
Right. No, I don't think sensors are, I mean, in situ sensor, like at the mouth of a stream which is going into Mendota or what have you, or the Yahara River. No, I mean, I think there are, there's a monitoring network for Yahara Lakes, obviously, but I don't think it's something that's done. I mean, it's just, it's one thing I learned when I was in DNR. Everybody said, well, DNR does that, or DNR will figure that, but there's nobody. I mean, there really isn't. There's hardly anybody doing a lot of this work. So if it's a specific project and it's focused on, some best management practice in that watershed, maybe there's a sensor there, but I don't know of any. And then the first part of that, I still don't quite understand what you were asking. Should citizen science?
Now, you added a part to my question about that first.
Shoot.
But yes, should citizen scientists attempt to contribute photographs when they see something?
Oh.
And the other part is water samples, so it's cheap tests for saline for salt, for other known things. So when you take that picture, you take a water sample.
Yep.
And maybe there's a 50-cent test or some process of bringing in the expense is gathering all the samples in the right scientific way.
Right. So, I mean, the state does have this citizen science program, and there's these water monitors. I mean, you can take these classes, and they'll teach you how to collect samples, properly, without, putting your thumb in the bottle kind of thing, and where to send the samples. And you can sign up for that kind of things, and they have different levels. You can get different badges or something and move up the chain. And so there is a whole program for that. And, I think that's between DNR and Extension does a fair amount of that work. I do know, because it turns out there's GEO also has a citizen science working group, and One of the people happens to be at UW at the Nelson Institute. I can't remember her name now, but she had just put me in contact with another woman with United Nations, who's also the co-chair. But there's a lot going on in citizen science and how they can collaborate with groups like us. There's a lot of neat smartphone apps that are being developed now that take pictures of these these phycocyanin blooms, and some are somewhat quantitative, but also they take pictures, and again they timestamp that and then you send it in. So there's some apps, and I'd be happy to share that with you. There's some really neat stuff happening, some neat innovations. Okay, anything else?
Thank our speaker.